I will switch to English also. So Sara prepared her PhD with Naïd, who is here in the jury, and Loïc Dorbec, who I believe cannot attend the PhD, but that's okay. So the jury is composed of Eva Delmatir, who is professor at the University of South California, and Taisuke Boku, who is professor at the University of Tsukuba. They were reviewer of the PhD, and they made a written report proving the defense of the PhD. And then the rest of the jury is composed of Alexandre Fender. Hello, Alexandre, who is online and who was a former member of Maison d'Assimilation. Marc Bouy here, who is professor at the University of University of Paris 8. And myself, Edouard Audy, a member of Maison d'Assimilation. So Sarah, you have 45 minutes to present your work, and then we will go through some questions.
Thank you. Hi everyone, thank you for being here, thank you for your presence. Today I'm going to present you my thesis work entitled High Performance Data Analysis for Road Traffic Control. So first I'm going to give you information about the framework. So it's the results of a collaboration between a company and a university, the company Eiffage, which is the third construction company in France, based in Europe, with a global presence, and the University of Paris-Saclay. The hosting laboratories are l'IPARAD, it's a laboratory for distributed computing parallelism, and la Maison de la Simulation, where we are right now. It was supervised by Professor Naïd, who is my thesis supervisor, and Loïc Dorbec, who is the director of New Nuclear at Eiffage Energy System. So in the company of Eiffage Energy System, this thesis was the result of a project named Route du Futur, World of the Future in English. It was a collaboration between many companies, Eiffage Energy System, Eiffage Route, Total, IFSTA, Alta Road, and this project was focusing on road innovation, traffic simulation, dynamic weighting at tolls, etc. So first, I'm going to give you context before presenting my contributions, the state of the art, the potential solutions for the challenges addressed, and an innovative algorithmic approach that I used for my first contribution, which is the Unite and Conquer approach. And then I'm going to present my contributions. So about the state of the art, right now in the literature we have many road traffic simulators based on the multi-agent paradigm. You have also macroscopic road simulations based on equation flows. It's not as accurate as the multi-agent traffic simulator, which are more modern, more accurate, but it comes with some challenges. You have the Sumo, which is open source, often used for small scale traffic simulation studies. MATSim, which is mostly commercial, Polaris by the Argonne Laboratory, and MATSim. We focused on MATSim because it is particularly representative of the other road traffic simulators in the literature. It's particularly representative and maybe the most used in the literature when it comes to multi-agent road traffic simulators. So as I said, it's widely used in the academic research. Also, it's used by government agencies, companies, government agencies, etc. But it comes with some computational limitations. We have scalability issues because, as I said, it's very accurate. You can simulate each agent individually, so it takes very long time to process, to have a convergence, because MATSim is an iterative process. I will explain after why. So it requires a lot of memory, so it's almost impossible to run it on a domestic computer. And it's mainly sequential. Most of them are mainly sequential. You can find some multi-threading or parallelism, but it's very sporadic, and they don't take advantage of the latest architecture hardwares. So our objective during this thesis was to propose efficient solutions to accelerate the multi-agent traffic simulators by bringing algorithmic innovations to take advantage of the most modern hardware architectures like multi-threading and distributed computing. For that, we relied on representative enough multi-agent traffic simulators which is MATSim, which I will present after. And one important goal that we had, it was to enhance the scalability, because we focus on the road traffic simulators, which simulate a large-scale areas. So what is MATSim? MATSim is the acronym for Multi-Agent Transport Simulation. So it's an open source simulation tool. It's for large-scale areas. It's used primarily for simulating the travel of behavior, individual agents. It was developed in 2004 by the TU Berlin, and it's still developed there today. Also in CNRS Lyon in France and in other international institutions. It's an activity-based model. That means that each agent has a daily plan for 24 hours. And these daily plans are created thanks to data from census data from the cities, etc. And all the agents have a route choice. They can make decisions based on personal preferences or economic choices, etc. So for MATSim, particularly MATSim, you have a population, and a geographical area. Each agent has a plan for the day, for example, leaving home at 6:50, going to work by car, etc. So as I said, all the agents start their day with a plan, as I said, based on some data from census data from cities, 24 hours. Then you have the simulation over 24 hours. So they just execute their plan. Then you have a scoring. Each plan after one simulation over 24 hours is scored. For example, if an agent arrives too late to an activity, the score will decrease. Or if the agent arrives too early, it's the same. You have a loss of time, so you will have a lower score. But if the agent arrives on time to an activity, the score will increase. It's a very complicated function, so I didn't present it here because it's not very useful. And then you have the replanning phase. What is the replanning phase? It's a phase where you can just adjust the plan. For example, leave later or earlier to avoid traffic jam, or choose to go by car instead of public transport, etc. So this is a plan, a daily plan. It's illustrated here. It's usually you have an XML file with all the plan for all the agents for simulate for a scenario. So here, for example, you have an example. This is a video from YouTube for MATSim Singapore. You have an agent leaving home, so it's the white square, stuck in the traffic jam. You can see that the agent evolves among other agents, thousands, millions of agents sometimes. And the agent goes, for example, to work. And you can see here, you have a utility score, the score I was talking about before. Here the agency is late, so you can see like the score is decreasing here. It's just an example. About the replanning model I was talking about before, here you can see the illustration of daily plan. You have an agent leaving home at 7:30, for example, going to work by car, then going to shopping or going to laser. You can see the score is not very satisfactory. Like, it's not very a good score that the agent had here. So MATSim will apply some strategies, just as you would do in your daily life, to have a better, efficient management of your time. So for example, here you can see that the agents leave home 20 minutes after. Maybe the agent avoids traffic jams, and the score is better here. Or you can have other strategies. Here, the agent goes walking to work. You can see the score is not very good, etc. So as a user for MATSim, you can choose the distribution of the weight, the replanning strategy weight that you will apply to have different generation of plans. Here is the best score because throughout the iterations, MATSim will just create plans and store it, another plan, store it with different strategies, and each plan has a score, so you can have a big weight for selecting the best score, or reroute, just changing the itinerary for your activity. The time, you can change your departure time, and transport mode, taking car by car public transport, for example. And you have this process again and again through many hundred simulations until you reach a convergence. This is the average score throughout the iteration. And after here, you have only 30, but it's not what's happening. In fact, you need, as I said, many hundred iterations to reach the convergence. Convergence means that all the agents are adapted to each other in the same environment. So what are the potential solutions? Because as I said, MATSim is a good tool used by many institutions, agencies, companies, but it's very slow and not very efficient in terms of computation. You can bring some HPC techniques in terms of implementation, multi-threading, for example, using GPUs, and you have some results in the literature about that, some promised results, but they're incomplete. And the other focus is the algorithmic innovation. This is what we choose to do. Rather than solely optimizing implementation, we just considered introducing new algorithmic strategies. And we choose one strategy, which is named Unite and Conquer, developed by Professor Naidemad. So we could address the algorithmic challenges with the first contribution. So now I'm going to present briefly the Unite and Conquer approach. So the core concept of the Unite and Conquer approach is that you have multiple iterative methods, referred as co-methods, and so you can solve large-scale simulations. It's primarily used for linear systems or problem of eigenvalues in a complex computational environment. The key benefits of this approach is that it's adapted to the modern hardware architectures. You can maximize the use of the resource, and it's scalable. It's effective for large-scale computations. Here is the divide and conquer approach. So it's different. It's not like I present this so you don't confound it with the divide and conquer approach. In the divide and conquer approach, you have a problem. The problem is the puzzle, for example, and you divide it into sub-problems, and you have the same function, the same method to solve the sub-problems. In the Unite and Conquer approach, is different. Each method has the whole problem, and you have different methods. For example, Mickey Mouse will resolve the problem differently than Goofy or Donald or Minnie Mouse, and they will, throughout the iterations, give to each other tips and solutions to solve the problem. So the fundamental principle of the UC approach is that it has asynchronous communication, but also synchronous communication. But with the asynchronous communication, you can reduce latency by overlapping the communication with computation. You have less bottlenecks. It's fault tolerant. That means that if one method fails, the other process computation continues. And there is heterogeneous parallelism. The co-methods may have different types of parallelism, multi-level parallelism, distributed computing, multi-threading, etc. So, as I said before, after each cycle, the co-methods exchange information to select the best one based on predefined criteria. And it's particularly efficient in many problems. It's used also in cybersecurity, for example. It enhances the performance for large-scale simulations, and it's particularly beneficial for multi-agent traffic simulation since it requires efficient hardware and good algorithm. The first contribution, now I'm going to present my first contribution, which is entitled multiMATSim. So what is multiMATSim? It's a variant of MATSim that incorporates the Unite and Conquer approach, so we can enhance more rapidly we can converge more rapidly to the solution and running less iterations. So, as I said, you have several MATSim instances that run in parallel, each one with a different distribution of the weights that I was talking about before. It's the only thing that differs from the instances of MATSim. They have the same scenarios, same population, but this distribution of weights let us generate different plan and explore a wider space of solutions. So again, at regular intervals, the instances exchange a plan. They all have different plane, and after each 50 iterations, step iteration, for example, they just exchange the plan, and based on some criteria, they will exchange the plan they found and go again with another 50 iteration or whatever. The name of the parameter is step, so I will explain more precisely just after. So to resume, you have two nodes, for example. It's an example with only two instances so you can understand better. You have two nodes, the node X and the node Y. Both have, for example, the MATSim Los Angeles scenario with the same population, the same geographical area, Los Angeles. So on node X, you will have instance I. On node Y, you will have instance J. And the only thing that differs between the two instances is that they will have different distribution of nodes. For example, instance I has this distribution, and instance J will have another distribution. This is just an example. So this is what's happening. In instance I, you have the agent AK and the same agent in instance J. At the beginning of the simulation, both have exactly the same plan. You will run MATSim for step iteration, let's say 50 iterations, then you will have a stop. Because of the different distribution of the weight strategies, you will have different plans generated, so they explore a wider range of solutions. And they will, for example, instance I will just check if the instance has the best score for this agent. It will continue with another step iterations. It will also exchange the plan with instance J. If instance J has not the best score, that means instance I has the best score. So there is a calculation with standard deviation to check if the difference in terms of score is really high or small. If it's small, it will just continue with its plan. If it's too high, it will just get the plan of the instance I with the best score and continue the computation over again with another step iterations. And we have this process again until we reach a convergence. So the conceptual explanation for multiMATSim, it will be the same for the unite and conquer approach, is that you have a distributed optimization, you have a collaboration among the instances, so you have a more robust exploration of the solution space. You have a pooling of collective resources, which is the agent plans. So you have a superior problem solving. Philosophically, you can compare it to collective intelligence and swarm optimization. So one instance is, for example, an autonomous agent probing disparate section of the solution space, and you have parallel and interconnected processing. Theoretically, you mitigate the risk of the convergence to local optima since you share it periodically. So the benefits of multiMATSim compared to MATSim, as I said, you have a faster convergence, it's more scalable, and you have a better robustness. So now I'm going to present the results that we had with multiMATSim. So about the methodology that we use, first we wanted to compare the execution of MATSim with multiMATSim with 4 instances and the scenario of Los Angeles with 0.1% of the population. That means approximately under 20,000 agents with synchronous communications. Then we wanted to assess the horizontal scalability by increasing the number of instances. More instances means more nodes, more hardware. We wanted also to assess the vertical scalability, by increasing the number of agents, going from the scenario of 0.1% to the scenario of 1% with 10 times more agents, and the combination of both. So to validate the approach, we assessed the convergence speed and the simulation accuracy. And for the computational performance, we assessed the scalability and the execution time. We had the honor to test our experiments on the WUSH and Fugaku supercomputer. Both have different CPU architectures. For the WUSH, you have the Intel Design Gold, which is based on x86 architecture, whereas for the Fugaku, you have for the CPU on Fugaku, you have the ARM architecture. So these results are only on Russian. I will talk about the results on Fugaku later. So here, I would like to draw your attention on one thing. So here, you have the average score executed throughout the iteration. So you have an illustration of the convergence. Here, you have the traditional MATSim in black, and the colored curves are for the instances of multiMATSim. So here, you can see that the score is increasing until converging. One thing that you have here is just an artifact, because in MATSim, after 80% of the iterations, here for 300 iterations, you can see at the iteration 240, you can see that we have a sudden jump. It's just MATSim taking the historical best score of all the E-agents together. This is not an important thing. The most important thing is how it's evolving the convergence. And you can see the same jump here, because every time we have a stop, as I said before, and in the traditional MATSim, you don't have any stop. So the squares can be explained like this. So let's say here you have the convergence. You can see that the score starts to stabilize here after 6 hours here of computation. So the score here, you can refer to the score 105 to have a score of convergence for this scenario. And you can see that with the MATSim instances, because they immediately explore a wider range of solution, right after the first exchange, we reach the score after only 1 hour and a half. So we have here a speed up of 4. We tried also with 8 instances, doubling the number of instances to check if we could have a better speed up, but it's not the case. Even with 8 nodes and 8 instances, we reach this score and go beyond this score right after the first exchange, so after 1 hour and a half. So, but we kept in mind one thing: the jump you have here after the first exchange is higher than with the 4 instances, so we just kept that in mind. So we went until 300 iterations. One important detail is that in MATSim, you don't have a stop. It doesn't stop. You, as a user, choose the number of iterations that you want, and you check visually on the graphs where is the iterations after which number of iteration you have convergence. We choose 300 because on the GitHub of Los Angeles MATSim, you have 300. So by default, it's 300 iteration, and we just kept that. So the MATSim Los Angeles scenario with only 0.1% of the population takes 8 hours on rush with the CPU I mentioned before. As I said, it's only 0.1% of the population. With 1% of the population, you need something like 40 hours. But as I said, it's not parallelized. It's mainly sequential. With the multiMATSim LA 4 and 8 instances, it's approximately the same. It's even longer. But here the goal is not to accelerate the execution time for one iteration, but to accelerate the convergence process. And this is what we achieve to do. And again, another thing is that with the 8 instance configuration, we don't have better results, but we have a higher jump after the initial data exchange. So maybe we were thinking at first, maybe if we have earlier exchange, we could have better results in terms of convergence, time of convergence. Here we tried with the Los Angeles scenario with 1%, so 10 times more agents, almost 200,000 agents. We can see that we have the same result, approximately the same result, the same behavior. So we have a speed up of almost 4.8. So we can say that maybe we have enhanced scalability in data intensive environments. We tried also with the 8 instance with change every 50 iteration. This is the step variable. Exactly the same higher jump here with 8 instances. We wanted then, after, as I said before, we wanted to assess if we have maybe an earlier exchange with more instances, maybe we could have better results. And we tried with the Los Angeles 0.1 scenario. And this is exactly what happened. With an exchange every 25 iterations, here we have the first exchange after 45 minutes instead of 1 hour and a half. And we can see that if we refer again to the score of convergence for this scenario, 105, we have here, we reach the score after only the first exchange, so after only 45 minutes. We can say we have a speed up of 8 instances, speed up of 8. For instance, speed up of 4. We don't have enough data to check this proportionality, but we can assume that maybe we could have this with more instances. And we wanted to save some hardware resources, so we tried also this configuration, but only with 4 instances, but we didn't have the result that we wanted. We need 2 exchanges, so same amount of time, so this is not very efficient with this configuration. So this step value influence needs more work to check if maybe we could have better relationship between the number of instances and the speed up that we can have. About the experiments that we made on Fugaku, we had very unexpected results, because for one iteration for the Los Angeles 0.1% scenario with Rush, with the Intel CPU, one iteration takes approximately 2 minutes, but on Fugaku we had 10 minutes for only one iteration. But finally, the explication is very logical, because on the Intel CPU has a larger chip, more adapted for mainly sequential programs, whereas the A64FX CPU is smaller and more optimized for massively parallel applications. Other explanations, we have other explanations. For example, in the literature, we found that on the A64FX, you have better performance when you have the libraries compiled by Fujitsu. We didn't have the OpenJDK because, again, MATSim is in Java, and the problem was with MATSim. And since multiMATSim relies on MATSim, this is why we had this bad results also with multiMATSim. But again, it's proper to MATSim. So when you don't have the libraries compiled by Fujitsu, sometimes you have poorer performance, and we didn't have the OpenJDK compiled by Fujitsu. Maybe you could have better performance with that. And maybe MATSim is not optimized for ARM CPU architecture. We didn't have the opportunity to check it with another CPU, ARM computer based on CPU architecture, so it's a possibility. So with a faster convergence and a better accuracy, the experimental results validate the multiMATSim approach compared to MATSim with faster convergence and, as I said, again, simulation accuracy. And about the parallel computing advantages, we can say that multiMATSim outperforms the traditional MATSim in terms of scalability and then time execution. It's a superior choice for large-scale simulations. Our first goal was not just to optimize MATSim. We wanted to optimize, to bring a new approach for the road traffic simulation in general. So we started with MATSim because it was representative enough of road traffic simulation based on multi-agent paradigm. We tried with other scenarios, Ile-de-France, Berlin, with the same amount of agents approximately, and we had the same results. But it's necessary to try it with other road traffic simulators such as Sumo, Polaris, or MATSim, for example. Now I'm going to present the second contribution, which is based on AI and surrogate modeling for multi-agent road traffic simulation. So again, the thesis problem statement at first was to find HPC or AI-based algorithmic solution to enhance the execution time and computational efficiency of complex multi-agent traffic simulators. And again, MATSim and other simulators like MATSim are very expensive in terms of hardware resources and time execution. So we wanted to assess the feasibility of using neural network to replicate the key outputs of MATSim. So again, as I said, we developed a neural network surrogate model to approximate the results of MATSim. First we used LSTMs, but finally we didn't have maybe not enough good results with LSTMs. We tried after the MLPs. That's why you cannot find in my thesis the results with MLPs, because I tried first with LSTM, but we had much better results with MLPs. And we started first with only a proof of concept. We tried to generate only a variable from the main output of MATSim, which is the daily plan of an agent optimized. So we focused on a discrete variable first. So you have in the daily plan of an agent at MATSim, you have many parameters. You have the geographical coordinates x and y on the card. You have the departure time, travel duration, mod shares, and routes. Mod shares is the different mode of transport an agent used throughout the day. So we transformed it as a vector. I'm going to explain. So let's say you're an agent. You go to work in the morning, so you take your bike to go to the public transport station. Then you take the public transport to go to work, and you go back home by public transportation. And again, you take your bike to go home. So you took the public transport twice, and you took your bike twice. And again, when you go back home, you have the shop next to your home, not very far, so there is no traffic jam, for example. So you take your car to go to shop and go back to work. So you have the car 2 times, public transport 2 times, and bike 2 times. But with MATSim, after several hundred of iterations, after assessing how you evolve with other agents, maybe you don't have any traffic jam, so you will change based on preferences, economic choices. You will just take your car to go to work because you don't have traffic jams. You will go back to home. you will go back to home, and on your way you'll just stop to the shop. So you will take your car 3 times. You will have this vector instead of this one. This is something that can happen with MATSim and always happens with simulation of MATSim. So this is a vector, the information that we have about an agent and his daily plans, about the mode shares. So we created a scenario, a small scenario. Again, we wanted just to have a proof of concept. So we created a small scenario. We just extracted daily plans of 1,000 agents from a bigger scenario, the 1% scenario of MATSim. And we created 7,000 inputs. We generated the outputs with MATSim executions. And we wanted to make sure that the neural network captures the interdependency between all the agents in a scenario. So one entry for the neural network was composed of the daily plan of 1,000 agents. So we wanted something very simple to try it, to test it first. So we kept the minimal data. We kept only for the input per agent. We kept only the total distance traveled for the day and the transport mode vector. And for the output, you just have the transport mode vector, because it's the thing that interests us at first. So about the data split, we had 70% for train, 50% for validation, 50% for test. We had on test data, we had the MAE of 0.05 and MSE of 0.01. So this value indicates that the model performed reasonably in predicting the modified transport mode vectors. Here you can see the residuals. So you can see that most of the residuals are in 0. You have some negative and positive residuals, maybe because of the simplicity of the model. That needs some improvements, but the results are reasonably good. So again, as I said, it's maybe too simple. Maybe we need further investigation to understand how well this approach generalizes beyond tested scenarios and variables. The next steps may include trying to generate other variables and other discrete variables and other continuous variables, so we could have the whole plan and the whole main output of MATSim. And we would like to scale it up also to have with higher scenarios, because again, it was on a smaller scenario with 1,000 agents, because again, it was just a proof of concept to try if it works. So about the conclusion. So we wanted to modernize traffic simulations because simulators like MATSim exist since almost 20 years. So we recognize that it has a growing importance, and we have now the autonomous vehicles which are coming in the traffic. So we need tools like traffic road simulators, accurate enough to manage more efficiently the traffic. We wanted to exploit the latest technologies advancements. We focused on the algorithmic design and high performance implementation to have improvements, and we tried also the surrogate modeling with AI to approximate complex processes like road traffic simulations. So the perspective with MATSim will be to try it with much more instances, because we tried only with 4 and 8. Maybe it will be good to try with more instances, try a different variable of the step value to have a correlation between speed up and number of instances and the step value. And maybe we need to try it with higher scenarios, for example, the 10% Los Angeles scenario, or the 100%, for example, other cities. About the neural network, there are also a lot of things to do to improve it. As I say, just starting with a whole scenario first, a whole scenario, even 0.1% one, trying to have much more variables to have the whole plan at the end. So another perspective would be to combine the use of AI through neural networks with the unite and conquer approach. For example, when you have a neural network, you have the weights that are with the retropropagation, which are updated every time. And with the unite and conquer approach, you can distribute this exploration of solutions, for example, to converge more rapidly. Again, sorry, here I'm going to talk about my personal thoughts. As you all know, we are witnessing an era where AI and HPC are profoundly transforming various domains, including complex simulations like traffic modeling. AI is an approximation tool, so some people think that AI will replace everything. Some others think that AI is just a tool for approximation and cannot replace complex simulations tools. In my opinion, I think AI will change many things again. We are just in the beginning, and I believe it holds the potential to gradually replace many complex simulations, like road traffic simulations based on the multi-agent paradigm. So I had 4 publications in different conferences throughout my thesis time. You have the references here. I had the opportunity to go to Riken in Japan 2 times, thanks to the CEA and NDLS collaboration. Last time was in Kobe in Professor Mitsuhisa Sato's team with Miwako Tsuji. And I had the opportunity to go back this year in Mohamed Wahid's team in Tokyo in the High Performance Artificial Intelligence System Research team. Thank you for your attention. Special thanks to Professor Naidemad, who is my thesis advisor, Loïc Dorbec, Stéphane Bodlock, and Jean-Michel Bateau, who were my industrial thesis supervisor, one after other, in FH. William Jalby and his assistant, Director William Jalby, and his assistant Isabelle Miltner in l'IPARAD, second laboratory. Pascal Tremblin, the director of La Maison de la Simulation, she's not here today. Martial Mansib, who helped me a lot with the repetition and who is helping us right now. Valérie Bell, the assistant. And Mohamed Waib, Mitsui Sasato, Miwako Tsuji in Japan, who helped me a lot through my 2 contributions. And the jury members, thank you so much for being here. Thank you for coming from very far. And thank you for reviewing my thesis. That's all from me.
Thank you.